Now we're going to take a look at ordered symbol table operations using the binary search tree data structure as the underlying implementation. Well, each one of these operations are fairly straightforward, but just to check our ability to manipulate this data structure, we'll take a look at each. Suppose we want to find the minimum key in a binary search tree, or the maximum key. Well, just looking at one example, you can see almost immediately what to do. To find the minimum, we move left from the root until we find a null key. That's where the smallest key in the data structure is. To find the maximum, we move right from the root until we find a null key. What about floor and ceiling? Well, those are a little bit more complicated, and we'll have to, not quite the same as in the ordered array for binary search. So we have to do a little bit more work for that. So just for example, let's take a look at the problem of computing the floor. So what we want to find is, so say we're seeking the floor of G. So that's the largest key in the data structure that is less than G. In this case, the answer is E. So let's just take a look at what we have to do in the tree, the path we have to take in the tree to figure that out. Well, so we're looking for the largest key that's less than G, and we have S. Well, that key is definitely going to be in the left subtree. It's not going to be bigger than S because S is bigger than G, so we go to the left. So now we're sitting at E, and so what's the largest key that's less than G in this tree here? Well, it might be E, but there's no way that it's to the left of E because those keys are all smaller than E and therefore smaller than G, so E's a candidate. But it might also be in the right. So we move to the right in this case. So that's if K is equal to the key at the root, the floor of K is K. If K is less than the key at root, it's in the left subtree. That's the one we just did. If it's greater than the key at the root, the floor of K is in the right subtree if there is any key smaller than K in the right subtree. So in this case, there's no key smaller than G in the right subtree, so therefore the answer is E. So our code has to check for these three cases. And here's the code that does it. It's not that much code, it's just complicated code to understand. So if we find our key, that's the floor. If we're going to the left, we find the floor of the one on the left. And on the right, we have to do a little bit of tricky code to make sure that we return the floor in the right subtree if there's some tree there. If there's no node there, then we return the root itself. So that's a implementation, but that code is definitely tricky. And there's similar code for ceiling. So now, what about operations like rank and select? How many keys are there less than a given key? And give us the seventh largest key. To facilitate implementing those operations and also size, all we do is keep an extra field in each node, which is the number of the nodes in the subtree rooted at that node. So this tree's got 8 nodes in it. This subtree has 6 nodes in it, and so forth. And those counts are going to not only enable us to immediately implement the size function, just return the count at the root, but they'll give us good implementations of rank and select. So let's look at those now. So we add a count field to every node. And then to implement the size function, well, if it's null, we return 0. So a client might call us for a null tree or an empty tree. Otherwise, we return x.count, which is the number of nodes in that subtree by definition. The way we maintain, there's a number of ways we could maintain the thing, but the one that we'll adopt uniformly because it adapts to more complicated situations is just before we're done with the put operation, we'll say, okay, we've done all our work, and before we return a pointer to the given subtree, we're going to take the size of what's on the left and the size of what's on the right and add 1 for us, and that's going to be our count. So whether or not there was a new node added, we don't have to test for that. This recursively takes care of the problem of maintaining the size in every node when there's a new node inserted. And it also handles more general situations, as we'll see later on. So that's how to maintain size. So now how do we implement rank? Well, it's a little like floor. It's an easy recursive algorithm, but there are 3 cases. So let's look at the 3 cases. So we want to know the number of keys less than k. So we're going to have a recursive algorithm for our given key. So one of the easy ones is if our key is equal to the key at the current node, then the number of keys less than our key is the size of the left subtree of that node. So if we're looking for the rank of E, say, how many keys are there less than E? There's exactly 2. That's by definition in the data structure. That's the number of keys that are less than E. So that's that one for rank. What about starting at the root? If we have the case where E is less than S, so the rank of E in this whole tree is the same as the rank of E in the left subtree. So that's that case. And then if we're going to the right, then we have to add 1 for the root and 1 for the left subtree of the root, and then find the rank of us in the right. So that's an easy recursive algorithm for finding out the rank, and it's definitely an instructive exercise to check that you believe that that method works. The other thing we have to do is iteration, and iteration is a fundamental operation on tree structure, and it's based on so-called in-order traversal. And that's also a simple recursive algorithm. Traverse the left subtree, NQ the key, traverse the right subtree. So to iterate, we're going to maintain a queue of keys, and then we're going to call this recursive in-order method, and that method is going to add all the keys in the tree to the queue, and then we'll just return that queue, and queue is an iterable data structure, and the client can iterate that. And in order is just a simple recursive method. Put everybody to the left on the queue, then put the root on the queue, then put everybody to the right on the queue. And to believe this method, you just have to think recursively and prove by induction that this in-order method puts all the keys in the data structure on the queue in their natural order. First, it puts all the ones to the left on the queue. If that happens in their natural order, then the next thing that has to appear is the key at the root. And then if the ones on the right go in their natural order, and then by induction, they're all in their natural order. That's a very simple implementation of an iterator for the symbol table with comparable keys. So you have to, again, prove that property by induction, and that's easy to do. And the diagram at the right gives another simple way to look at it pictorially. All the keys that are smaller on the left, we're going to put them out, and then we put the key at the root, and then we put all the keys on the right out in order, and then that key is going to have all those keys in order by induction. So here's the operation summary for ordered symbol table. And the quick summary is that every one of those operations, well, ordered iteration is optimal. It just gets them in linear time. And all the rest of them take time proportional to the height of the tree. Now, if the keys are inserted in random order, we know that height by analysis is going to be proportional to log n. or if it's some application where the order of insertion of the keys is well modeled by random order, and that's not unusual at all. Binary search tree is a simple and extremely effective data structure that can support all of these operations quickly, much better than binary search in an ordered array, which is not dynamic and slow for insertion. So that's a look at binary search tree implementations of ordered operations when keys are comparable.